So take down today's topic, magnetism and electromagnetism. And let's go to the first slide. To start off the game, right, we're going to pretend that someone has just donated money to you to start off your dream business. Choose a box. Now, when you choose the box, you cannot change your mind. Send it on the screen and you have to stick with it. Today, when you make choices, no matter if it's a bad choice or a good choice, you have to stick with it. All right. So let's see how much money that you all got, right? Some of you all are going to be disappointed, right? All right. Some of you all are starting off with $200. Some of you all are starting off with $5, and some of you all are starting off with 100,000. Don't worry. Good things can happen while we play this game. Sometimes you start off with a little bit of money, then you get plenty, and then you have some people who start off with plenty and end up with nothing. So write down the value that you got on your sheet of paper. All right? Somebody said it, the $5 is $5 more than they had before. All right, so write it down, right? And it can't change your mind. So let's get to the first thing here, magnets. I think everyone here has seen a magnet at some point in time or have played with a magnet. And we all know magnets have a North Pole and a South Pole. And around a magnet, you just have these invisible magnetic fields. Quick question. Well, before I give you the question, a lot of times in the exam, just for 1 or 2 marks, they will draw magnets in different combinations, and you have to draw the magnetic field around it. Now, you don't get too much marks for it, but 1 mark or 2 marks, it's still marks. If you have a bar magnet by itself, how do magnetic fields go? From north to south or south to north? How do magnetic fields flow? One person said north to south. And I think a lot of people are saying north to south, and that's actually true. So in the exam, all you have to do is just draw a few lines going from north to south. Now, one thing to note, right? The magnetic field lines, they radiate outwards. Now you notice I have the arrow. You notice as we go outwards, the lines, the loops will keep getting larger and larger and larger. Now, sometimes in some textbooks, the examiner is too lazy to draw the really big ones. So you will start off the big one and just show you where it's completed. Like this one here. He's too lazy to draw the big one, and he's just showing it's coming back to the South Pole. So you have to imagine the continuation. Quick question. As you go outwards, right, you notice the loop is getting larger and larger and larger. As you go outwards, does the magnetic field get stronger or weaker? What are your thoughts on that as you radiate outwards? Right? And I think that's common sense, right? As you radiate outwards, it gets what? Weaker, right? Because the further and further you move away from a magnet, the less effective it is. So as you radiate outwards, it gets weaker. Now, when they ask you to draw the diagram, you don't have to put in the weaker part. You just have to draw a few of the fields going from north to south. You're good to go after that. All right, so everyone take down the first diagram, please. All right, so let's say now we put 2 magnets next to each other. You notice we by now know that opposite poles attract. North is attracted to south. Like poles repel for sure. So what's going to happen for sure is that there's going to be magnetic lines going from north to south. Definitely, because magnetic lines flow from north to south. So for each one of them, you can probably just put one line. You don't have to put too much. But isn't there also a north pole here and a south pole here? Won't there be magnetic field lines going from north to south here also? Because magnetic lines flow from north to south. And how about this north here and this south here? Won't there be a magnetic line going from this north to south? So it's almost like you're connecting all the north to south combinations. That there will give you full marks in the exam. Take down that one. You're just connecting all possible combinations of north and south. So let me know when you're finished with that one. Okay. So let's look at the next slide here. We have a next combination over here, right? You notice this time it's not a north facing a north. It's a north, sorry, it's not a north facing a south. This time, like poles, two north poles are facing each other. Well, this one here is normal, right? Well, what's going to happen? There must be some magnetic lines going from north to south. So in each one of them, you just put what? A north to south. Right. But remember, like poles repel, right? So if you have to draw a big one, you just draw a big one like this. But I want you to draw it slightly different. You see this big one here? I want you to give the impression that it's being pushed away. So don't draw it nice and looped like that. Draw it like this instead. So it will look like it's getting pushed away. Draw it almost straight, like it's getting pushed to the side. Everyone understands that? It wasn't nice and outwards. You want to give the effect that it's being pushed away, right? So don't draw it nice and curved, right? Over here, you could draw it curved when it's far away. But in this little region, draw it kind of straight going upwards and then looping back like this. Right? Right? I think the examiner will appreciate that you're trying to show the effect that the two magnets are being repelled, pushed away from each other. And over here, we have a horseshoe magnet. You don't have to draw all the lines, right? Like how you have 1, 2, 3, 4, 5, you could just draw 2 here. Over here, you have a north to south, a bend one, you could just draw 2 of them. And of course, these are the big loops. The north, the examiner is too lazy to draw this, and it's coming back over here. And over here is a north. Examiner is too lazy, going back to south. The point is, the field lines are being connected in all possible combinations from north to south. Let me know when you are finished, right? You have 2 diagrams to draw here. I believe I have 2 more combinations to show you all, right? This one here, where the magnets are on top of each other rather than what? Side by side. So I think the obvious combination here is that you're definitely going to have what? A north to south and a north to south here for sure, right? North to south, north to south. There must be a big one, a big loop going up, and I'm too lazy to draw the entire loop, so he comes back here. Same thing over here. You can draw a big loop, and of course, pretend you're too lazy and just continue the loop here. Now, won't there also be a north to south here? And a north to south here as well. But also, you notice the north and south here. So you have to connect these 2 as well. And this one goes upwards from north to south. All right. Sometimes people draw one on the side here, kind of curved one going from north to south. But this and this is basically the same. And this one here from north to south, right? So some people like to draw the curved one. It looks a little bit fancier, I guess. All right. So I guess you should draw in the curve one as well. Take down that one, and then we'll do the last combination here. This is when the north and south are opposites. The north-south, and the other one is, sorry, this one is south-north, and the other one is north-south. One. In this one here, it's almost the same situation. You're going from north to south. You could draw one of the big ones here. North coming down to where? South. 1 second. Right. This one here, and of course, you're going to have a north to south here. This one definitely a north to south. North to south. Draw one of the big ones. Coming back to the south. Right? See if I'm going to forget out anything here. Now, you do not know. Some people might say, hey, you have a north here and a south here. So I should draw a line going from this north to this south. I would say that's common sense, but upon researching, I realized nobody draws in that combination. And I can't figure out why, to be honest, right? So just to be safe, let's just leave out that particular combination, right? I looked everywhere, like a lot of diagrams on the internet, and it just doesn't exist. All right, so this is a diagram for this particular one. I just want to make sure I haven't forgotten out anything. Doesn't look so. All right. One thing to point out, some people might not know this, but the Earth is a magnet, right? You will notice something strange, right? I think everybody knows where the North Pole is. That's where Santa Claus lives. And the South Pole is where the penguins live. You will notice something strange. All the time, I have been saying that the magnetic field goes from north to south. But look at this diagram. The magnetic fields are going from south to north, okay? Why is that? It's a mix-up of terminology. You see, when we say North Pole, we are talking about the geographic North Pole. And when we talk about the South Pole, obviously we're talking about the geographic South Pole. But the Earth is a magnet. And in case you all didn't know, you can pretend it's a magnet like this, right? A bar magnet. But over here, the North Pole is B and the South Pole is B. In other words, the North Pole, where Santa Claus lives, is actually a magnetic south. So the top of the Earth is actually southern, and the underneath of the Earth is actually north. So whenever you're talking about North Pole or South Pole, you have to be very specific, especially in physics. Are you talking about geographic north, or are we talking about magnetic north? Because magnetic north and geographic north are actually on opposite sides of the planet, right? So if you did not know that the Earth was a huge magnet, now you know, all right? So draw this diagram. You don't have to draw all the lines. You can just probably draw 2 or 3 on each side, okay? Let me know when you're finished with this. And of course, draw the little bar magnet here also, and show that the underneath of the Earth is a North Pole and the top of the Earth is a magnetic South Pole. So let's get to the next slide here. Right, now remember you started off your business. Some people started off with $5. Some people started off, I can't remember all the amounts. I think some of you were like $100,000, something like that. It's the first month of your business. Choose one of the colors and let's see what happens to your business. Choose one color and you cannot go back on it. A lot of people are saying blue. The minority of the people are saying green. All right. So remember your color, right? Whichever one you choose. Let's see what happens. On the first month of your business, for those who chose green, you made a very good investment in a cafe. So how much ever money you have, multiplied by 40. That's the new amount of money you have. For those who chose blue, you made an okay-ish investment in a bakery. So take the amount of money that you had at the beginning and multiply it by 5. And that will be the new amount of money you have. The aim at the end of the class, we're going to see who has the most amount of money. All right? Great. Keep track of it on that blank sheet of, the scrap sheet of paper, right? So how much ever money you have now, pretend it's real and it's in the bank, right? So, right, keep track. Let's move on. Okay, so what are magnets? We know magnets attract certain types of metals. We know magnets can attract. We know magnets can what? Repel. But if you ask somebody, well, why is a magnet a magnet? They're probably not going to what, be able to give you a good explanation. They're just going to probably say, hey, well, a magnet is a magnet, the end. And of course, you leave there just as confused as when you went in there. First of all, there are 4 materials on the CSEC syllabus that are attracted to metals. Usually when people say which metals are attracted to magnets, most people just say iron. But steel, nickel, and cobalt, all of them are attracted to what? Metal. So make a note here. Iron, steel, nickel, and cobalt are all attracted to magnets, not just iron, right? So make a note there. So let's not go to the magnet as yet, right? I want to investigate. Let's just take iron, the simplest one that we're all familiar with. We know iron is not a magnet. We know iron is attracted to a magnet, but iron is by itself is not a magnet. Quick question. If you take a magnet and you have a north pole and a south pole, and I break it in half, so I take this magnet and I break it into 2 pieces. Will the magnet stop working? Well, what are your thoughts on that? Use a little bit of common sense here. I take a magnet and I break it in half, right? The answer is no, right? Instead, you will just get 2 smaller magnets. And if I take this magnet and I break it up into 2 smaller pieces, well, then I keep getting what? Smaller and smaller what? Magnets. Eventually, if I keep breaking it in half, eventually, I will reach a point where I reach the atomic scale, and I will have a magnet so small that I no longer can break it in half. In other words, you will end up with the very, very, very possible smallest magnet ever. At that point, you call that type of magnet magnetic dipoles. Dipoles, this is how you draw it on a diagram. You draw an arrow. That's a symbol for a dipole whenever we're speaking about magnets. The arrowhead is north, the tail is what? South. So magnetic dipoles are a magnetic north and magnetic south that are separated by a small distance. You see this distance between the north and the south is so small. It's considered to be on a subatomic scale, meaning that from here to here is just like the distance from here to here is probably just one atom. It's literally that small. So I want you all to take down the definition of a magnetic dipole, because they will, well, not will, but they most likely will ask you that in the exam. It's at the end of the day, the magnetic dipole is the world's smallest possible magnet. Okay? Okay. But that still doesn't explain what a magnet is, right? It still doesn't explain it. You all will notice something, that the symbol for a dipole is an arrow. And forces represented by arrows, like, and whenever you have to draw a force on something, and it is draw an arrow to show the direction of the force. The arrow is not just to say north and south, it's to say the direction, right, of the magnetic force, okay? Tell me something. If I had a box, right, and I asked someone, a group of people, to push that box, and one person pushed so, and next one jump on top, and he started to push downwards like a madman. The other one push his foot underneath, he squeeze his foot underneath and start to push upwards. Then somebody jump kick it here, then somebody jump kick it in this direction, and somebody put it like this, and some other fool roll and hit it on the top here. Do you think that box is going to move? Do you think this is a good way to push that box? Right? Yeah, somebody call them. Well, I won't repeat that. All right? I don't think that box, even if that box moves, that box is not going to move far, because everybody is pushing in a different direction. There's no unity over there, right? So the forces don't add up. In fact, the forces start to act against each other. So that means, right, when you put iron, steel, nickel, and cobalt underneath a microscope, you're going to see dipoles, right? But the dipoles are going to be in different directions. So I have to take my time and draw this properly, right? That's not 1 second, right? So you might see some arrows over here going like this. In this area, you'll see some dipoles going here, dipoles here. But when you look over here, they're in a different direction. Down here is a different direction. But let's give it a few seconds here. And then you have some people here. You notice this come like the situation where we're trying to move the box. All the dipoles, right? Each section is pointing in different directions. So do you think all the magnetic forces, remember each dipole is a small magnet, but do you think the magnetic forces are going to add up here and do anything useful? What do you all think? Do you think anything useful is going to happen here? No, right? And this is why a piece of iron or a piece of steel, nickel or cobalt, that is why they are not magnets. Let me clarify this. Being magnetic is, sorry, being attracted to a magnet is not the same thing as being a magnet. So steel, iron, nickel, and cobalt, all the dipoles are facing in different directions. So nothing useful happens. So it is not a magnet. However, when you take a magnet, you investigate it, you will notice something. Look at what happens in a real magnet when you look at it underneath a microscope. You notice all the dipoles, when the majority of them, I mean, you must have one or two who doing what they want, right? But you notice the majority of them are facing in the same direction. And that's the main difference between a piece of iron and a magnet, okay? In a magnet, all the dipoles, or the majority of them, are facing the same direction. So it comes like, if you had to relate this to a box now, in a magnet, everybody pushing in the same direction. There's unity. So the box will move because all the forces add up, right? They work with each other, okay? And one thing, you notice that, let's go back to the iron. You notice in this area, everybody is facing the same direction, and everybody in this area is facing the same direction. So when you look at a piece of iron, right, and you look in certain areas, everybody in a certain area, there's always be facing the same direction. These individual areas are called what? Magnetic domains. And this is what the green box is saying. It's this green box, right? It's just basically saying that a magnetic domain is a specific region. And if you look in that region, all the dipoles will be facing the same way. Take down the definition also of a magnetic domain. Domains have dipoles. Dipoles are the individual magnets. And of course, draw the two diagrams here to show the difference between a piece of iron and a true magnet. Let me know when you're finished with everything on the screen, please. I don't know if you're picked up on this small detail over here, right? Didn't we just say that a magnetic field goes from north to south? I think that was on a couple of slides before. But look at the dipole. You'll notice the direction of the arrow from south to north. Anybody picked up on that? All the time I'm saying the magnetic field goes from north to south, and then the dipole goes from south to north. Why is that? Let me explain why. If we have a bar magnet, so this is the whole magnet, north to south. Outside the magnet, it goes from north to south. But remember, this is a loop. All loops have to continue. So if you continue this pattern, outside the magnet, it goes from north to south, but inside the magnet, it goes from where? South to north. Remember, this is the actual magnet. This is inside the magnet. So I guess I should have clarified that at the beginning. Outside the magnet, it goes from north to south. But inside the magnet, it goes from south to north, the opposite, because you have to complete the loop, right? There are minor detail. It's going to be important later on, but I was going to say it later on, but I said, let me just get it out of the way now. All right, so let's move on. Let's see what's next. All right. 1 second, I should have said something here before. One thing that I also forgot to mention is the only difference between a piece of iron and a magnet is the direction of the dipoles. So remember, dipoles are physical things. They're small, like atoms, but it's still physical. So if you could take a piece of iron, and you tell all the dipoles in the iron to get their act together, to face the same direction, the piece of iron will change into a magnet. That's the only difference between a piece of iron and a magnet, you know, right? You just have to find a way to get all the dipoles to face the same direction. And there are 3 ways we can do that, right? There are 3 ways we can actually convince the dipoles to face the same direction. That is what the next slide is about. Here are the 3 ways. If you have a piece of iron and you want to change it into a magnet, you could just rub the piece of metal with a strong magnet, but you have to rub it in one direction. You can't rub it back and forth, right? You rub the magnet or run the magnet along the piece of iron in one direction. You see, as you're rubbing it in one direction, you'll be convincing the dipoles to face one direction, right? But if you go back and forth, you'll do and undo the directions. Another way is that I used to do this one when I was small, right? If you only have a piece of metal, like a piece of iron or a piece of steel, and you want to make a magnet, all you have to do is take that piece of iron and hit it with a hammer, but you hit it in one direction. You can't hit it, well, as my mother would say, all how, right? So, and believe me, you could do this home now. You could take a screwdriver and take a hammer and hit it in one direction, just one way. Like try to hit it to the right. Do it about 20 times, and then take the screwdriver and put it by a paper clip. It will attract the paper clip. It will change into a magnet. It's real easy to do. Creating magnets, real easy. Or 3, you can take a battery, like this, you have a nail here, which is a piece of iron, right? And all you have to do is wrap a wire around it. Now you're keeping the insulation on it, and you're keeping the rubber on the wire. You're not peeling the wire, as they would say. Anytime you take, the whole point here is that current will come out the battery and make its way around the iron. It will make loops around the iron. Whenever you do this, you get something called an electromagnet. But the type of electricity that you have to put is direct current. Direct current means the current is only flowing in one direction. So direct current, the current flows in one direction. The opposite of a direct current is something called an alternating current. Don't worry, that will be on the next slide or a couple of slides down. But just make sure you state it just like this in the exam. Make sure you tell the examiner that you're applying a direct current in a loop around the iron. A loop is called a solenoid. That's just a fancy name for wire when you wrap it in circles, a solenoid. Right? And those are 3 ways you can create a magnet if you don't own a PS3 or a Nintendo set. Okay? All right, so on this slide, I was showing you how to create a magnet. But suppose you want to destroy a magnet now, okay? How to demagnetize a magnet. In other words, how to destroy a magnet. You're basically going to do the opposite. You could just take the magnet and just start to hammer it, but not in one direction. You just start to hammer it in all set of different directions, right? Or you can take the magnet and remember the diagram with the battery just now, and you wrap the wire around it. You can pass, instead of passing a direct current, you pass something called an alternating current through it. An alternating current is where the current flows in 2 directions. We'll get to that in the next slide just now. Or you can heat the magnet. Whenever you heat a magnet and let it cool down, by the time it cools down, it will no longer be a magnet. Take down the 3 ways to destroy a magnet, please. Let's see what's next. Oh, we have a little cutscene here. Right. So remember, you have to choose a color again. And remember, you have a new amount of money. The last set of money is how much you have right now, right? So which one do you all choose there? What's going to happen to your business in the 2nd month? Both could be good, both could be bad. One could be good, one could be bad. Cannot change your mind. So far, green is the winner. A lot of people are choosing green. All right, so let's see what happens. What fate your company meets. For those who chose green, you were robbed. you lose 80% of your money. So that means how much ever money you have, multiply it by 0.2. Because if you were robbed of 80%, then you're just left with 20%. So for those who chose green, how much ever money you have, multiply it by 0.2. All right. For those who chose blue, some wealthy person donated $50,000. So for those who chose blue, add $50,000 to your money and update that scrap paper. Right? Xavier, you have $5 now. Oh, shucks. All right. So you can see what happens in business, right? Sometimes you can start off with plenty of money, and then things just happen, and you end up with less money. And then some people start off with less money, and you talk to them a few years later, and they're millionaires. So, all right. So be honest with your calculations, right? Don't worry. You can get robbed now, but for all you know, something good would happen later on. Right, so let's move on. So here we have an electric bell, right? This is going to take a little while to draw, right? Now, let me just explain how the electric bell works. First of all, this here is a battery, right? Like a Duracell battery or ever-ready battery. Right now, pretend everything here is metal. As this diagram stands exactly how it looks in front of you, will any current be able to flow right now? What do you all think? I don't think so either. The answer should be no, because there's a gap in between here and here. However, when I press this button and this moves forward, there will be a connection between here and here. So now current can flow. So pretend current coming out the positive side of the battery, flowing and flowing, and making a loop over here. Now, when the current starts to flow around this, it will change into an electromagnet. The current flows up here, down here. There's a contact in between here and here, and it goes back to this side. Because this is a piece of metal, and this is now a magnet, this will be attracted to this. Everybody agrees with that? That this piece of metal will now be attracted to the electromagnet because current is flowing. And of course, when it moves forward, it's going to hit the gong. That is what will make the bell sound, right? Ding. But there's a little problem. When this moves forward, will there be any contact between this yellow plate and this pointy point? Well, pointy point. The answer is no. So when this actually moves forward, because there's a break in the circuit now, there's no physical connection here, current will stop flowing. Anytime there's a break in the wire or a break in connections, current cannot flow. So when this moves forward to hit this, no current can flow, and this stops being an electromagnet. But what we have here is a spring. When this stops being an electromagnet, the spring would pull it back in place. But here's the problem. When it pulls it back in place, it will make back contact and current will start back to flow. And he will move forward again. And of course, it keeps making and breaking the contact over and over and over. And of course, during the process, you're going to hear ding, 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 ding like that, right? Everybody understands that process, that effectively you are making and breaking the circuit. And by making and breaking the circuit, you are creating the noise. How much people, I'm not asking if you could word it, but does everyone here, can you all visualize the process? Let us get that out of the way first, right? So you understand the process. But obviously in the exam, if they ask you to word that now, like write a paragraph explaining that, how much of you all could honestly say that's going to be a little bit challenging? Because plenty times You can understand a process, but when it's time to write it, like me, I get serious problems, right? So I have worked on the actual wording here. I need for you all to draw the diagram. And if they ask you to explain it in the exam, this is exactly what I want you to write. And write it in steps 1, 2, 3, and 4. Read through from 1 to 4. Make sure you understand it. You will see it's the same exact thing we spoke about. When you read it through and you understand it, let me know in the chat that you understand it, and then take down everything on the screen. But I'm giving you a full 5 minutes for this, right? Wording things I know is a challenge. I know because I grew up having challenges with wording things. Oh, well, since that was such a long thing to take now. All right, so look at how much money you have now. Make another choice, green or blue. All right, so let's see what happens here. All right, so for those who chose green, you invested in a space program, and it was a very good investment. Take whatever money you have and multiply it by 700. So that's a really good investment. Sorry to say, an earthquake for those who chose blue destroyed your office. You lose 75% of your money. So if you lose 75%, that means you're left with 25%. So take whatever money you have for the blue people and multiply it by 0.25, because you are only left with a quarter of your money. So do the relevant calculations and update your financial records. Congratulations to those who chose green. Thanks, Jordan. Thanks. I'll hold you to that. See what's next. All right, so before we move further, well, we're going to cross the boundaries now. We're going to go from magnetism to electromagnetism, right? That's where electricity and magnets are mixed into one. There are two types of current, right? Usually when you have a battery, we know this side is the positive side, right? One side will be the positive side, and the other side, as you all know, is the negative side. If you take a piece of wire and connect the positive to the negative, we normally say the current flows from the positive side to the negative side. And the majority of people will say that, right? So this is how current flows. The symbol for current, by the way, is the letter I, not C. In physics, it's the letter I. However, when you, in real life, current doesn't actually flow from positive to negative. Whenever you're just pretending that current flows from positive to negative, it is called that conventional current. That is what we normally assume. But in real life, right, current actually flows the other way. Actual current flow is from negative to positive, right? But I just let you know, for whenever we do calculations or we do any set of theory, the norm is to assume it's conventional current, not actual current flow, right? So take down both here. Conventional current flow is the imaginary one, the one that doesn't happen in real life, but is the one we accept. Don't worry about why we accept the wrong way. Even if you accept that the current flows the wrong way, it doesn't affect your calculations. You'll get the same answer, right? So take down both notes, draw both diagrams, and we will move on. Let's see what's next here now. All right, so remember before we were talking about direct current and alternating current, right? Direct current is when the current flows in one direction. So if you had to draw a graph where the y-axis is current or voltage and the x-axis is time, you have to make sure the graph stays above the x-axis. Anytime, how it works, right? Anytime the graph is above the x-axis, that means the current is flowing one direction, right? Like in a battery, the current, we're talking about conventional current, the current will flow in one direction. But the opposite of a direct current, and this here is a symbol for an alternating current, is whenever you have a piece of wire and you connect it to something producing an alternating current, the current will flow one direction and then afterwards it will reverse directions. And this is how you draw it on graph paper, right? Usually just have it like this. Pieces be above and pieces be below the x-axis. Whenever it's above, it's assumed that the current is flowing one direction. When it dips below the x-axis, it means the current has reversed direction, right? So take down everything on the screen there, including the diagram. All right. Now here's the thing, right? You see, current and magnetism, they are closely linked. Whenever there's a current, somewhere around there's a magnetic field. The two is usually come as a pair. So anytime you have a piece of wire, right? Let me say we have a current running through this wire. The magnetic field around the wire is be circular. Now, it is be rotating in a circular pattern. To figure out the direction it rotating, you just use something called the right-hand grip rule. All you have to do is grip the wire with your right hand, obviously, because it's the right-hand grip rule, and your thumb points in the direction the conventional current is moving, the one that we normally call current. And the current is always be rotating from the back of your hand, your knuckles, all the way around your fingers. So anytime that you use this rule to figure out the direction of the magnetic field, like how it's rotating. Now, on the screen here, right, the good diagram, this is a side view. Let's say you were to put your eye over here. So your eye goes underneath here. So you can see if I can imagine it here. This is the ears here, and this is your head, right? And you look from this direction, from the underneath. Will you see the length of the wire, or will you only see the thickness of the wire? Well, what do you all think? Would you see the length of the wire or the thickness of the wire? Right, you would see the thickness of the wire. So this diagram here, you see this circle here, that is going to represent this point of view. And this here is the thickness of the wire. So whenever you are viewing the thickness of the wire, obviously the current could be going away from you. And if I reverse the current, it will be going towards your eye. Whenever you see an X, that means on paper, the current is going inwards. You need to know that, right? So whenever you see an X, the current is going into the paper. Whenever you see a dot, that means the current is coming out of the paper and into your eye. Everybody understands that? So when and the X can mean anything. If they're talking about magnetic fields and you see an X, that means the magnetic field is going into the paper. Whenever you see a dot, that means whatever they're talking about is coming out of the paper. I want you to use the right-hand grip rule. Pretend this is a piece of wire. Grip it with your right hand and let your thumb point into the paper and tell me which direction the magnetic field will be flowing. will it be flowing anti-clockwise or will it be flowing clockwise? Reason it out, right? Pretend this is a long piece of wire going into the into the screen, and the current flowing into the screen as well. Right, so I'll wait for your answers. If you grip this with your right hand and your thumb is facing into the screen, right? Just a hold. Right. Remember, you're looking at the back of your hand. I think, I gave you all the wrong answer. It's supposed to be flowing clockwise. Look at it. When you grip it, you're looking at the back of your hand, no, not the front of your hand, because your thumb going into the paper. So that means you are looking at it from the back of your hand. It will actually go clockwise. Everyone who got it wrong understands? Amelia, you had it correct. And the other one, if you grip the one that's going out and your thumb is facing out of the screen, but then you have to look at the front of your hand. And in that case, it will be going anti-clockwise. It will be rotating this way. Remember, the current flows from your knuckles around your fingers. Right? It takes a little while to grasp, right? Since it's kind of hard to, and a lot of people, they usually have a lot of problems interpreting this, right? How to use the rule. Some people just choose to memorize it. Whenever you see an X and the current going into the paper, it's clockwise. And when it's coming out of the paper, it's anti-clockwise. So you could just memorize. Into is clockwise, out is anti-clockwise. Right? So take down everything on the screen. But this is the last note we're going to be taking for the day, but we have some homework that I need for you all to do. It's 2 very short videos, but I really, really need you to look at it before next week. And I'll explain why in a little while. All right, so let's get to what the homework is. It's going to be very, very simple, but super important for next week. There's a topic that I cannot teach on the screen, that I literally cannot teach using pen and paper. You need to see it in 3 dimensions. You actually have to see me set up some equipment and walk around the equipment. So I made a video for you guys in the physics classroom, right? When you go in the physics classroom, you just click on physics classroom, scroll down, and you will see 2 rules. Fleming's left-hand rule and Fleming's right-hand rule. Fleming's right-hand rule is completely different to the grip rule, the one that we just did. Please, I'm really begging you guys, please watch these 2 very short videos. They're like 10 minutes each or something like that. They're real short. But just don't watch them. You have to watch them, make sure you understand it, make your notes a real little bit of notes. If you don't watch it and give it your best shot, you're going to be real lost next week. Because remember I said, I literally cannot explain this using a sheet of paper. In this question, you will see it in 3D, a walking around the diagram. It's a live video. Everybody understands how crucial it is, and you understand what the homework is. Please, don't forget. Please, please, please don't forget, right? Because I think you all understand almost everything we did today. Let's not break that trend next week. And don't lose that sheet of scrap paper. Please put it in your books, and we will continue it next week, right? The game isn't finished. It's a long game, right? Take care, guys. I won't hold you back much more. And Khadija, you say you need to talk to me?